All right, so let's begin the process. I like to do this type of problems, guys, finding the critical points and the turning points and all these things into steps. So the step one, we're gonna call it finding the critical points, if any, because there may not be critical points, although in most cases there will be. You can rest assured in that in that case. Okay, so let's find the critical points of this function here. How do we do it? Okay, if you read the definition that I gave you here, that one, pause the video, read it again. You're gonna remember, you should remember that a critical point is where the derivative of the function becomes zero. So basically what I need to do is step one, find the critical points. I'm gonna write my function, and then I'm gonna find the derivative of the function. So this is very simple. F prime of x, it's gonna be 3x squared minus 12x minus 36, right? And then I'm gonna make immediately that derivative equal to 0. What does that mean? Since the derivative is all of this, I'm gonna write 3x squared minus 12x minus 36 equal to 0. And basically, this is a question that I'm posing. This is, you should understand this equation as a question. What I want to find is what values of x, when I put them inside the derivative, make the derivative equal to 0. That's what I'm trying to find. Since this is the derivative, I write it down, I make it equal to 0, and then I basically put myself to the task of finding the solutions to this equation, right? So I can find the values of x that make the derivative equal to 0. So we have this equation. All the terms are divisible by 3. So let's simplify the equation. 3x squared over 3, that's x squared. Minus 12x over 3, that's minus 4x. And this over 3, that's going to be minus 12. It's the same equation. This and this are the same equation, but this is simpler to solve. Then we have a quadratic equation. We can solve it with factorization, right? It's gonna be this, right? And so the solutions are gonna be x equals 6 and x equals minus 2. So basically, partial conclusion, the critical points are x equals 6 and x equals minus 2. This is the partial conclusion of step 1. Well, this is the conclusion of step 1. These are the critical points of my function. At these points, at x equals 6 and x equals minus 2, let me quickly sketch that for you. Suppose this is 6, suppose, no, that's not right. Suppose this is minus 2, suppose this is 6. At those points, guys, right there, my function will have the tangent, listen very closely, the tangent to the function will have its slope equal to 0, like this. You see what I mean? Or it could be like this, look, like this. Right at those points, at minus 2 and 6, I'm going to observe this, that the slope of the tangent to the function will become flat or horizontal. That's what's happening. That's what makes these critical points, right? Or, I mean, let me not forget about that. Or it could be this, like this, you see? Because also at this point here, the slope of the tangent is 0. Okay, so that's what happens at a critical point. This behavior of the function. Now the step 2, I wrote it already here. It's finding the turning points, if any. Now that we have the critical points, I'm gonna find the turning points. And basically what that means, guys, is that you have to make sure that these in fact are, I mean, we know that these points are critical points and they are the candidates to be the turning points, these two here, okay? They may not be turning points, but they could be. And how can we tell? We can do the following, right? The step 2, which is basically the following. Try to understand it very well what I'm gonna say next. You're gonna make a rough sketch of the plane, and I want you to put the two critical points, -2 and 6, more or less, right? You don't have to do it very precisely. Then I want you to put guidelines, vertical guidelines here at those points, -2 and 6 at my critical points. There you go. And then you're gonna select over the x-axis any point on this section, any point on this section, and any point on this section, or intervals, right? From -infinity to -2, you're gonna select any point. Then from -2 to 6, another point, and from 6 to infinity, another point. Which points? Whichever you want, it doesn't matter. Try to choose a very simple integer. For example, over here in this section, I could choose the number -3, right? The simplest one. Then from -2 to 6, what integer could be simple enough? Could be the 0, right? And from 6 to infinity could be 7. And I want you to draw them like that. And we're gonna call these our testing points. You're gonna see why in a moment. These are the testing points, -3, 0, and 7. Then we're gonna carry out a process that I like to call precisely that, testing. And what I want you to do is evaluate the derivative in the testing points. F prime of -3, F prime of 0, and F prime of 7. Remember that we have the derivative from over here, right? This is the derivative, remember. This is my derivative. Let me actually bring it downstairs over here. Copy. So this is my derivative. You see? And I'm going to evaluate this derivative in these values, in -3, in 0, and 7. So basically, from in -3, that would be F prime of -3, right? And I'm just gonna put the -3 where it belongs, in the x's, right? And I'm gonna calculate this value, and I'm gonna put the result in here. The same for 0 and the same for 7. I'm gonna do it on my own, do it on your own, and let's get back with the results. Okay, so I did it and I got these values. F prime of -3 is 27, F prime of 0 is -36, and F prime of 7 is 27. Okay, and then listen next. I don't really care about what value I get. I only care about its sign. This is positive, so I'm gonna write this. This value is negative, so I'm gonna write this. And this value is positive again, and I'm gonna write plus, okay? And then, these guys, if correctly interpreted, basically solves the whole problem. Let's see how to interpret this testing. All right, so here we go. That was not good. Okay, so again, we already we agreed that at -2 and 6 we have critical points, so therefore my function may do this, right? Or may do this right there, or may do this. You see? Why am I saying this? Because at a critical point, the slope of a tangent, which I'm drawing right now, are horizontal. The slopes are 0. The same for 6, right? I may have either this, or this, or this. Got it? Let me clean this up. So how can we tell? How can we tell whether I'm gonna, at -2, I'm gonna get this behavior, or this behavior, or this behavior? How can I tell with this testing? Here we go. This is what you need to understand. In F prime of -3, the derivative is positive. And remember, the derivative, guys, the derivative gives you the slope of the tangent. So basically, I'm saying that at this point, at -3, right there, if I could draw the slope at -3, the slope is gonna be doing something like this. It needs to have a positive slope because of this. Okay, my tangent will have a positive slope. what that means is this, guys, that my function is doing something resembling this behavior. Take a look. It's going up, it's going up, it's going up, you see? Because, again, the slope of the tangent at -3 came out positive, you see? So therefore, what I'm saying is that the function is increasing until it reaches -2, right? And then, in this other section, from -2 to 6, the evaluation of the derivative came out a negative. So what that means is that at zero, the slope of a tangent is going to be doing something such as this. It's going down, the slope of a tangent. So my function must be doing this. Should go down like that, you see? So that at 0, when I draw the tangent, its slope is negative. So basically, this is a critical point, -2, that also turned out to be a turning point, because to one side the slope of the tangent is positive, this, and to the other side of -2 the slope of the tangent is negative, which is this here. Basically, the derivative is changing signs from positive to negative after you cross the critical point of -2, and therefore this makes this point a turning point. Okay, then for the same argument over here, we must have the following. At 7, the derivative is positive, so that means that when I draw the tangent to the function at this point, it should be going this way. It must have a positive slope, you see? So what does that mean? That 6 must be also a turning point, because the function goes from decreasing to increasing. You see what I mean? So basically, we have discovered already the turning points. The turning points are -2 and 7. What is -2? This is what we call a local maximum, like I said before. And this, at 6, we call it a local minimum. Okay, there you go. And then let me make another pause.